You might be wondering how a microprocessor looks like inside, how this small piece of device contains so much data and information. Do you know that microprocessor carries the arithmetic, logic, and control circuitry required for a CPU to function?
How? What exactly is contained within the microprocessor? Or should I say, what is the internal architecture of a microprocessor?
Hello, future engineers. We are the Group 1, and we are going to tell you about the microprocessor's internal architecture.
Most single-chip microprocessors use MOS technology or metal oxide semiconductor for gaining extremely high packing density required to fit a complete processor on a single integrated circuit. However, MOS is slow, and faster logic systems such as SCAT-TTL are not suitable for very high circuit densities. SCAT-TTL, a relatively fast bipolar logic family, normally produced in integrated circuit form, whose internal configuration is similar to normal TTL, except that SCAT-T transistors are used. That is why microprocessor must be built as a group of integrated circuits rather than a single pack. Other benefits accrue to the system designer by breaking down the processor into small elements. This includes improved control over the instruction set and the ability to incorporate high-speed logic techniques that are too complex to fit on a single-chip device. This chapter attempts to explain the fundamental internal architecture of a microprocessor as well as the various techniques that can be used when the MPU or microprocessor unit is divided into multiple sections. This chapter concentrates on what are known as byte-slice machines, a microprocessor which are available as a group of high-speed circuit elements rather than a complete MPU in one integrated circuit package. Now let's learn about our first topic, which is the internal elements of a microprocessor circuit. There are three basic building blocks of microprocessor. Those are the register, arithmetic and logic unit, and the control unit. Registers has two forms: an array of static memory elements such as flip-flops, or a portion of a random access memory or RAM. Static memory devices is RAM or static random memory access that retains data bytes in its memory as long as power is being supplied. Dynamic RAM. It stores bytes in cells consisting of a capacitor and a transistor. A microprocessor which uses dynamic memory techniques must be continuously driven by clock pulses in order to preserve data integrity. So what is clock pulses? Clock pulses is a signal used to synchronize the operations of an electronic system. Arithmetic and logical unit. The arithmetic logic unit is the part of central processing unit that carries out arithmetic and logic operations on the operands in computer instruction words. The arithmetic and logic unit usually provides at the minimum facilities for addition, subtraction, and complementation. Shift operations can be accommodated either by the data selector approach or by a shift register. It is a combinational digital circuit that performs arithmetic bytewise operations on integer binary numbers.
Enhancement to the microprogram control unit. Most commands are carried out by going through a series of micro-instructions that are normally stored at adjacent addresses in the microprogram ROM. In this case, just adding one to the present address suffices to create the next micro-instruction address, resulting in a reduction in the amount of microprogram ROM storage required to define the next address. However, an unconditional jump to the set of micro-instructions that test for an interrupt before fetching the next instruction is common at the conclusion of an instruction. It is important to provide the following micro-instruction address in greater detail in this scenario as well as many others. This is accomplished by charging the nano instruction to the no-op state on the CPE and forming the next address with other bits such as the condition select bits. From one processor to the next, the exact way this next address is encoded into other address fields differs. Microprogramming strength rests in its ability to condense complex operations like multiplying and dividing into a single instruction. Having the ability for one microprogram to use another microprogram on a subroutine basis is useful. This can be accomplished by giving a stack to the microprogram control unit for storing subroutine return addresses, like how a microprocessor handles standard software subroutines.
The microprogram for finding the square root of number c using the logarithm x is equal to 1/2 of x plus c over x would call the division microprogram subroutine in order to evaluate c over x. Figure 5.3 shows the typical bit-slice microprogram control unit.
Multiply and multiple shift require the execution of the same sequence of micro-instructions numerous times. A counter is used for this purpose, and the counter is loaded with the number of times the instruction will be repeated at the start of the instruction. The counter is decremented by 1 each time the micro-instruction sequence is executed, until at the end of the sequence, the counter 0 state is utilized to induce a microprogram branch out of the loop.
Figure 5.3 shows the typical microprogram control unit for a bit-slice machine. The address of the next micro-instruction can be selected from one of 4 sources. First, the micro-instruction itself, as with the simple unit of figure 5.3. Next is an incrementer, which adds 1 to the current microprogram address, and then the micro-instruction starting address ROM. Lastly, the push-pop stick used for storing micro-instruction subroutine return addresses.
Pipelining. Pipelining is defined as the starting the next job before the current one is finished. It consists of adding auxiliary timing registers at certain key locations so that the memories can be addressed in advance of their outputs being required. This technique helps to reduce any system slowdown which occurs as a result of memory access time. For example, in the simple control unit of figure 5.2, it would be advantageous to load the instruction register in advance of the beginning of the instruction cycle, so that when the cycle does begin, the microprogram starting address is already available at the data selector. In this way, the access time of the starting address ROM does not add to the overall system timing.
So for the last part of our report, I am going to discuss about simple example of microprogram processor and multi-chip microprocessors.
A simple example of a microprogram processor. So this shows the overall structure of a simple processor operating under microprogram control. Each instruction follows the state graph. The loop of instruction begin with state D through A and B are the normal state followed by each instruction and its convenient for explanatory purpose. To begin with state D, the sequence of events begin with state D as is follows. State D. Micro instruction switches condition selector to examine interrupt line. If line shows no interrupt, then next address selector selects next consecutive micro instruction address to give state A. If line shows interrupt request, next microprogram address taken from current micro instruction to give state E. State E. Program counter contents are sent out on address bus and incoming data is loaded into instruction register. State B. Program counter is incremented by 1 using the ALU and contents are returned via internal bus to the program counter. State C. Executive the instruction. Clearly, the microprogram of a particular processor is greatly influenced by the internal architecture of the processor itself. However, this flexibility is not always needed or desired, and a more limited approach is often preferred. Next is multi-chip microprocessors. First, let's define what is multi-chip microprocessor is. Multi-chip microprocessor. Generically, an electronic assembly where multiple integrated circuits, semiconductor dies, and other discrete components are integrated. In this section, it is necessary to draw the distinction between byte-slice machine, which allow variable hardware designs, and multi-chip processors, which have a fixed hardware design but permit by changing the microprogram norms. In its simplest form, a multi-chip fixed architecture microprocessor consists of 3 circuits. First, the central processor, which may have 8 to 12 or 16 byte capability. Second, the microprogram sequence control logic. Third, the microprogram ROM. Multi-chip microprocessors are used as built-in controllers. When a multi-chip microprocessor is switched on, the controller program stored in its internal ROM launches instantly. Another application for multiple chip microprocessors is in the design of a special purpose machine which require unusual instructions.